All right. Okay. So thank you very much for the introduction. I'm very happy to be speaking here. So everything I'm talking about is joint work in progress with Wei Xiao Lu, who's at Marseille, and Wei Zhang, who is at MIT. Okay. So as motivation, I'd like to start with the modular curve. So I'll fix the imaginary quadratic field f over q, and I'll consider the modular curve of level n, but base change to f. And so I want to consider some Heegner cycles. So I'll impose the Heegner condition, which is that for all the primes dividing the level n, I'll require all of these to be split in the quadratic field. And I also assume that the prime 2 is unramified. Okay, so given this, we can define Heegner cycles. So this z on the left here is parameterizing elliptic curves with Cm by the maximal order and say some fixed signature. And we can map this to the modular curve after fixing some ideal, which I've written as frac n here, some ideal of norm n, which exists by this Heegner condition. Okay, so given this Heegner cycle, there are at least two heights that one can consider. And so the first height is the Néron-Tate height as considered by Gros and Zagier. So this cycle defines a divisor on the modular curve or a class in the Picard group. But this Picard group has an action by Heck operators, so we can decompose so we can make a decomposition corresponding to modular forms. So if I fix f, a cuspidal new form of weight 2 and level n, then I can consider the isotypic component, the f isotypic component of the Picard group, at least after base change to C. And so this Picard group is a finitely generated abelian group because for pig 0, it's true by Mordell-Weil, and the Néron severity here is rank 1. And it turns out that because f is a cusp form, if I take the f isotypic piece, this is already lying in pig 0 in the subgroup of degree 0 divisors. Okay, so this f isotypic piece, so the z sub f on the left-hand side is my notation for the projection of z to this f isotypic component. And since it lies in pig 0, I can take its Néron-Tate height, which detects, so who's vanishing or not, detects whether this class is torsion in the Jacobian. And so the result of Gros and Zagier, stated in rough form, is that this Néron-Tate height can be related with an L function, namely the central derivative at s equal to 1 of the base change of this modular form f to the quadratic field. And so here, again, the center is at s equal to 1. Okay, so this is the first, maybe most famous height that one can take for this Heegner cycle. But there's another height that one can take, which is the Faltings height. So let me try to explain this. So one way to define it is in terms of the line bundle E of weight 1 modular forms. So this lives, at least over the open modular curve, lives like this. And so this 12th power is the bundle of weight 12 modular forms and has a canonical section given by the Ramanujan discriminant function. And so this Faltings height is going to be a weighted count of the points in the Heegner cycle by a certain norm defined using this line bundle. And this norm will be the Peterson norm. So there's a line bundle, and I'm supposed to give you a metric on the line bundle. And so to do that, I pick a section. So I pick the delta section, and I need to specify the norm of this section. And so here's the usual Peterson norm. And so to put that in a formula, the Faltings height of this cycle is up to some constant given by a sum over the complex points of the cycle, weighted by this interesting arithmetic function, the Ramanujan delta function. And so just like in the Néron-Tate height case, this height can also be related with an L function. So it's a classical formula of Lurch and Challis-Selberg that this is related with the log derivative of the quadratic character eta f associated to the imaginary quadratic field. And in this case, unlike the case of Gros and Zagier, this is at a non-central point of functional symmetry. So this derivative is taken at s equal to 0, while the center of the functional equation is at s equal to 1/2. And this is something that we observe also continues in higher dimension. Okay, so I presented these two heights here, and the talk will mostly be about the height on the right, on the Faltings height. But I'd like to explain how both of these can be viewed from the point of view of arithmetic intersection theory. So let me fix a regular integral model of this modular curve over spec OF. So usually this is over spec Z, but since, all the primes dividing the level are split in the quadratic field, if I take a base change, this does not destroy the regularity. Okay, and now there's some arithmetic intersection pairing. So this chow with a hat on it means some chow group defined on the integral model. And so this arithmetic intersection pairing is is evaluated in the complex numbers. And so both of the pairings on the previous slide, both the heights on the previous slide, can be expressed in this language. So the Naren-Tate height can be expressed in terms of a suitable lift from the Picard group to this chow group of the integral model. And so this is easy to state. So this Naren-Tate height here on the right is, okay, up to a sign expressible in terms of the self-intersection of this class and the arithmetic chow group. And so this is, in fact, this is some general fact about curves due to Faltings and Hyoyak, so not specific to the modular curve. Okay, and so the Faltings height can also be expressed as an arithmetic intersection number. So again, so z hat here is some suitable lift of the Heegner cycle to the arithmetic chow group, and E hat is also some lift of this bundle E, which is in the Picard group, to this arithmetic chow group. And so this arithmetic intersection number here has two terms. One involves the Faltings height, which I defined on the previous slide. And there's another term involving the integral of a so-called Green's function on the complex point of the modular curve. And so the first term, as I mentioned, is mentioned to the log derivative of an L function. And the second term also has some automorphic interpretation in terms of the derivative of an orbital integral, which the derivative of an orbital integral. And moreover, if we consider elliptic curves E with CM not necessarily by a maximal order, so by CM with a possibly non-maximal order, then there's an additional correction term related to non-Archimedean orbital integrals. And so for the purpose of this talk, I'll call this correction term heights of CMP divisible groups, which I'll plan to elaborate on later in the talk. And so one of the main ideas of the talk today is that all these three different terms on the right-hand side can be packaged together from the point of view of a relative trace formula into something relating with adjoint L functions. Okay, so I'll elaborate on this in a moment. I'd like to explain two things here on the right. So one, why is it natural to consider CM by non-maximal orders? And two, how to bring in the automorphic theory, since on the right-hand side, I didn't say anything about automorphic forms yet at the moment. Okay, and so both of these can be packaged together in the theory of Heck operators. So let me take X to be this modular curve for shorthand, and I'll consider the diagonal class, X going to X times X, which is the identity Heck operator. And let me also consider another Heck operator, T, in blue here. So I can view this as a cycle mapping to the self-product of the curve. Okay, so here's a diagram. So here's my X times X. So it's got two coordinates, so it's a box. And the diagonal here is drawn as the diagonal. And this blue curve, delta, is the graph of the Heck correspondence. And so these orange points are the intersection points of these two curves. And we can think of these as the fixed points of the Heck correspondence. Okay, and so now I like to count the fixed points. And so I'll count this in two ways. So I'd like to count the degree of the intersection. The first way is to decompose geometrically and to look at, to decompose this intersection geometrically. So for an example, let me assume P is not dividing the level. So I have a good Heck operator, TP. I'd like to calculate this intersection with a diagonal class. And so we can decompose these into CM cycles, which I've labeled Z phi here. So let me say what this is. So these phi's here are characteristic polynomials. These are integral polynomials with constant coefficient P, and where the linear term is undetermined. And this Z phi is a CM cycle, so parametrizing elliptic curves with CM by possibly non-maximal orders. So these parametrized elliptic curves E with some level structure, together with an endomorphism of the elliptic curve of degree P. So that's where the constant term of the characteristic polynomial is P. And in general, the intersection decomposes into some open and closed components indexed by these different characteristic polynomials. And so here, just to be clear, by the characteristic polynomial of gamma here, you can, for example, take gamma acting on an L-adic Tate module. So you'll get a polynomial of degree 2. Okay, so by analyzing these CM cycles, we can count the degree. And so roughly speaking, these cycles have degree given by Hurwitz class numbers. So this is not literally true because one still has to take into account the level, but okay, for example, in level 1, we can count them in this way. So on the right-hand side is h of the discriminant. So this is a Hurwitz class number counting binary quadratic forms of a fixed discriminant. And so so this also counts CM elliptic curves with CM by possibly non-maximal orders. Okay, and so this is something that one can do in general. So this degree of this intersection can be expressed as a sum over CM cycles. Okay, so as a sum over these Hurwitz class numbers up to something depending on the level, as well as some cuspidal contribution coming from cuspidal fixed points. So that's one way to compute this intersection number. But there's another way to compute this intersection number coming from Lefschetz's fixed point formula. So to compute the number of fixed points of this Heck operator, well, we can calculate its graded trace on cohomology. This graded trace equated by some sign, this Heck operator, is also calculating this the degree of this intersection number. And so this is then related to automorphic forms because we know that we can describe the cohomology of this modular curve in terms of automorphic forms. For example, H1 is described by weight 2 cusp forms. So we can re-express this graded trace from Lefschetz's fixed point formula in terms of automorphic forms or modular forms. So here there's a sum over, say, automorphic forms pi, and this Heck operator T is acting on, okay, so this cohomology has an eigenspace decomposition. And the Heck operator T acts on each eigenspace just by the Heck eigenvalues. That's the lambda pi T here denotes the Heck eigenvalue of T for the automorphic form pi. And there's some additional multiplicity here, which is the dimension of the k-fixed space of the finite part of the automorphic form. Or in more classical language, this is coming from the theory of old forms and new forms. So it has a explicit description in terms of the divisor count of the level n divided by the conductor of the modular form, say for H1. Okay, so just to summarize this example here, so I have this intersection number calculated in two ways. One is by geometric decomposition, and one is by something more spectral in terms of the automorphic theory. And so this is a special case, or an intersection theoretic explanation of a special case of the classical Eichler-Selberg trace formula, which relates these Hurwitz class numbers with a trace of Heck operators on spaces of modular forms. And so in more trace formula language, those Hurwitz class numbers, indexed by characteristic polynomials here, correspond to elliptic orbits in the trace formula. And those cuspidal terms, which I mostly ignored, correspond to hyperbolic orbits in the trace formula. Okay, so this maybe is a really key example for the talk, where we have some intersection theoretic quantity, which we compute in two ways to extract an interesting identity. So one side is these class numbers, one side is this information about modular forms. And so what we'll do in the talk is replace this degree, this count of intersection points, with something fancier from arithmetic intersection theory. And so for this, it's a little more convenient to rephrase the spectral side in terms of the diagonal class. So this is what I'll do next. So this diagonal class lives in the child group of the self-product, not to be confused with Ramanujan delta. And this child group, so just like before, has action of Heck algebras. So there's one Heck algebra on each factor of x. And so we get an isotypic decomposition of the diagonal class in terms of representations, one from each factor. And so the diagonal class has some symmetry here, and it turns out that we should only get pairs of representations which are dual to each other. Okay, so this is a spectral decomposition of the diagonal class. And so now I want to do something similar for the Heck operator. So if I consider this Heck operator T, which is supposed to be a cycle class on the self product, you can re-express this as in terms of as a Heck translate of the diagonal class. So this T tensor 1 here just means I apply the Heck operator T in the first variable, and in the second variable I apply the identity Heck operator. And okay, so if delta is supposed to have this spectral decomposition indexed by automorphic forms from the previous line, then I should be able to calculate this Heck action on the diagonal class in terms of the Heck eigenvalues. So that's this expression on the right here. So I can re-express this Heck trans of the diagonal class in terms of some weighted sum of the isotypic components, where the weight is expressed by these Heck eigenvalues.
Hi, Ryan. May I ask a
Yes,
question?
hi. Yes, of course.
The TX on there, that why they don't have other terms, it's just the diagonal terms.
Why it doesn't have? Okay, so first, okay, so here I have the diagonal class which only has those dual terms. So is your question about why there's only the dual terms?
No,
Why
that's
pi must?
okay. But there, when you TX on there,
Yes.
do you get some other terms too when you T shifted the diagonal to somewhere else?
No. So what happens is, so I move this t inside the sum, so it acts term by
Mm.
term on the sum, and so this t acts on the first factor pi, so I get a Heck eigenvalue, and then the identity acts on the second factor, and I just get one.
Oh, okay.
Yeah.
Thanks.
So yes, no problem. Thank you very much for the question. Okay, so now I have these spectral decompositions of the diagonal class and the Heck operator. And so I can use this to calculate the intersection pairing. So this point count, the degree of the intersection, okay, we should be able to calculate this as an intersection product in the Chow group. And there's supposed to be some adjointness for these Heck operators with respect to the pairing. In other words, the self-adjointness means that these different Heck eigenspaces should be orthogonal to each other. So if I calculate this intersection pairing, I should be able to calculate the intersection on the isotypic pieces term by term. So the Heck operator T, contributes a lambda pi, and otherwise I get a self-intersection class for these isotypic components. So if I compare with the previous calculation of the trace in terms of cohomology, I'm saying that these self-intersection numbers, these isotypic components, should correspond to these dimensions from before. And so the reason I bring up this diagonal class formulation is that it's this formulation of the self-intersection which is more easy to generalize to the setting with an arithmetic intersection number. Okay, so I'll move to the arithmetic intersection number next. So here's the formula from the previous slide copied for reference. So it's exactly the same. Okay, here's this picture from before. And so now what I'll do is replace this degree, this point count of the Heck fixed points with a weighted point count, which is the height. Okay, so here it is in the bottom left, at least formally very similar. So let me explain the terms. So in the middle here, I have this height. So it's this weighted point count of the intersection numbers. So the weight is by this Faltings height that I mentioned earlier, essentially. And so, more formally, this is defined by an intersection pairing, by a trilinear intersection pairing on the self product of this curve x. So x times x is dimension 2 in the generic fiber. The integral model, you get something 3-dimensional, so it makes sense to pair 3 divisors on the integral model. And just like before, at least formally, one expects to decompose this intersection number in 2 ways. So the first way is by analyzing the sort of physical intersection. So we decompose the physical intersection into CM cycles, and we take their height. Okay, and again, there's some cuspidal contribution, which I'm ignoring here. And the second way is to consider the spectral theory and decompose over automorphic forms. So that's this bottom line here, where it's the calculation, at least formally, is very similar to before, where we replace this intersection number in the Chow group with some high pairing in the arithmetic Chow group, where this H is defined like here in the trilinear pairing, where we insert the line bundle. So just like before, we think of this as a geometric and spectral decomposition of a single quantity, this intersection number. And so the point of this talk, or the title of this talk, is that these quantities now should be related with adjoint null functions. That these self-intersection numbers should be related with adjoint null functions, at least in the case of unitary Shimura varieties. Okay, so so if there's no questions here, maybe I'll move on and try to explain what I mean by this a little more precisely. Okay, so I'll move on. Okay, so now let me try to state the relation with adjoint null functions a little bit more precisely. So I'll take a unitary Shimura variety, which I'll call X. So here X is associated essentially to a unitary group, except there's an additional factor. There's an additional torus factor here, which is convenient for integral model reasons. But for example, in the complex fiber, I take the Schmurr variety of this group. It's just going to be a disjoint union of Schmurr varieties for the usual unitary group. So it's something as a mild change from the usual Schmurr variety for unitary group. And I'll take this this indefinite signature n-1, 1. And okay, for simplicity, to state the conjecture and theorem, let me assume that I have this child group of the product is semi-simple as a Heck module. So in the case that we need, we'll prove this, but in general, I'll say it this way to formulate the conjecture. So, okay, as I mentioned, I'm considering the diagonal class. This lives in middle degree, in other words, in degree codimension n-1 of the self product. And so I'm assuming that this decomposes semi-simply for the Heck action on each product, just like in the example from before. So just as before, delta is supposed to decompose, at least formally, as a sum over isotypic components. And so to abbreviate, I'll just write delta pi for the pi isotypic component, or the pi times pi dual isotypic component for this Heck action on the product of x times x. Okay, so now I can state the conjecture in rough form. So if I take pi in automorphic representation of the unitary group, so let me assume this to be cuspidal, cohomological. So here cohomological means a cohomological of middle degree, appearing in middle degree cohomology of this of X. And stable, so I want the base change to be cuspidal. Then the height pairing, the self-height pairing of this diagonal class should be expressed in up to simpler factors in terms of this log derivative of the adjoint L function times something times this dimension of the K fixed space. So just to be clear here, the adjoint L function is an automorphic L function associated to pi, where the representation of the L group, here the L group, the connected part is just GLN. The representation of the L group is just the adjoint action on this Lie algebra given by conjugation. And so there's also a special value. Okay, this is in terms of the derivative. There's also a special value version of this, where the derivative in the numerator becomes a special value. Then there's then the numerator and denominator they cancel, and you recover this dimension count that I mentioned earlier from just the geometric count of the fixed points. Okay, so this is our expectation. We don't know how to prove this in general, but so before I move on to that, so I want to point out here that just like in the beginning with the Faltings height, this derivative is taken at a non-central point of functional symmetry. So the center here is at s equal to 1/2, and here we're taking derivative at s equal to 0. Okay, and so we don't know how to. Is there a question?
So yes. The height of delta pi. Is there an issue defining it if the Schmurr variety is non-compact?
Yes. Okay, yes. So yes, definitely. Technically there's definitely an issue. So I mean, we need to use these Burgos-Kramer, these BKK child groups, arithmetic child groups. But okay, so for what we can actually prove at the moment, we restrict to the compact case. We restrict to the compact unitary Schmurr curves. So in general, one can arrange it to be compact if we work over, as you know very well, we work over a totally real field, then then you can avoid this compactness issue. But yeah, so there's definitely some technical issues. Yes. Okay.
Sorry.
Yes. No problem.
Right. Well,
yes.
We also have some term contribute from the torus in the Schmurr data.
Yes, those will be yes, okay, but those will but not on the level of not on the level of intersection theory. So this will contribute something simpler, just like a class number factor. So not significantly, but so yes, there will be some contribution, but
I see. Thanks.
Yes, no problem. Okay, but so what we can actually prove is the case of n equals to 2 for compact unitary Schmurr curves in the case of good reduction. So it's unfortunately not possible to, over Q, it's not possible to arrange for this Schmurr variety both to be compact and have every good reduction. So I'm asking for too much. So so we don't prove a result at the primes of bad reduction. But more precisely, what we actually prove is a precise equality at all the primes of good reduction, and then there's some ambiguity left over at the primes of bad reduction. But over a totally real field, which I've omitted here, it's possible to arrange for this Schmur variety to be both compact and have everywhere good reduction, in which case it should be possible to remove these correction terms. But for today, maybe let me just stick to this case over Q. Okay, so later in the talk, I'll say more about how we prove this. But before that, I just wanted to mention quickly maybe why it's reasonable to expect that adjoint L functions have something to do with these diagonal classes, or maybe at least middle degree cohomology. Okay, so if I look at middle degree cohomology of this x times x, so middle dimension here is n-1. We expect that it's a general expectation that the L function of the cohomology, the Schmur variety, should be describable in terms of automorphic L functions. And there's supposed to be a piece corresponding to pi times pi dual, explained by a recipe of Langland's. And this representation, maybe let me not say what it is more explicitly, but it decomposes as two other L functions associated to the base change of pi to gln over the quadratic field. So here, this AS means ASI, so these two ASI L functions, is an ASI plus and ASI minus L function. And this adjoint L function from the previous slide is exactly half of this. So it's exactly one of these ASI L functions up to a sign where the parity depends on, the sign depends on the parity of n. Okay, and so this adjoint L function is somewhat half of an L function that's expected to occur in the cohomology of this product. Just as a very basic example, let me consider the case of n equals to 1. So I'll pretend that the Schmur variety is just spec f, so spec of the quadratic field. This might not literally be true. There could be some class number and some level and so on. But for illustration purposes, let me just pretend it's just a point, spec f. And so pi will be an automorphic representation for the unitary group, this rank 1 unitary group. So it'll be some character. And if I look at the L function of cohomology here, okay, middle degree, this thing is 0-dimensional, so middle degree is h0. This is just given by the Dedekind zeta function for the quadratic field. We know that this factors has just the usual zeta function times the L function of the quadratic character for this quadratic field. And this is exactly the decomposition from the previous block. So this zeta function here is the ASI plus L function from above, and this L function of the character here is the ASI minus L function. These correspond exactly to the decomposition from before. And okay, so our conjecture and theorem is about sort of half the L function, only the adjoint L function. And so this is completely analogous to an average version of a conjecture of Kolmez. Okay, here over a total, which really applies over a totally real field, over a Magic quadratic field, not much of an average. In any case, this conjecture predicts that faulting sites of CM abelian varieties after average over the CM types should be expressed in terms of the log derivative of the L function of this quadratic character, which is exactly this ASI minus L function here, which corresponds also to the adjoint L function, adjoint L function from the previous block. So in some sense, this average conjecture of Kolmez, okay, which is now a theorem, is is corresponding to n equals to 1 case of our conjecture. And so our work and for higher n is somewhat complementary. So we definitely don't give a new proof of average Kolmez, but we prove something complementary for higher n. Okay, so next I'd like to say something about the strategy. How do we actually prove this relation with adjoint null functions? So the strategy is by a relative trace formula. So here's a cartoon of what I was describing earlier. So I have this arithmetic intersection number, this height pairing, which is being calculated in two ways. So one way is to do something geometric and analyze the intersection points, the CM cycles. And the other way is to do something spectral and look at decomposition over automorphic forms. Okay, so the theorem theorem and conjecture is about relating this height pairing with adjoint L functions. And so the relation will be by comparing this with another trace formula. So there will be another trace formula for this Flicker-Rawlins pair of GLN, compared GLN embedded into GLN over the quadratic field. And there will be some distribution here, which decomposes also, again, in two ways. So there will be some geometric, so-called geometric decomposition in terms of orbital integrals and trace formula language. And there's another decomposition here spectrally indexed by automorphic forms. But here, just as before, we should get a weighted sum of these Heck eigenvalues of some Heck operators, where the weight is by these adjoint L functions. So how the proof actually goes is that, well, in the standard trace formula way, to compare the geometric size of the trace formula, something that may be more calculatable, we make a comparison between heights of CM cycles and orbital integrals. And from this, one should be able to deduce that the spectral sides match. And so to get an equality term by term for each pi, so the standard strategy is to use linear independence of characters. These lambda pi of t's should have some linear independence, which should allow us to extract a term by term matching of this height with the adjoint L functions. So at a very rough level, this is the overall strategy. Okay, so so far I've mostly focused on the left-hand side, the intersection theory side, but next I'll say something more about the analytic side, the right-hand side. So I won't say too much here, but I thought I should at least define maybe what are these orbital integrals that I'm considering. Okay, so we consider a relative trace formula here, the right-hand side. So here's the setup. I'll consider the group H as just GLN, and H prime is this GLN over the quadratic field. So this Flicker-Rallis pair. F will be a test function on this big group, and I'll take W to be the space of length n row vectors, which has right action by this group GLN. I'll take phi to be another test function on this affine space. Okay, now associated to all these test functions, there's the standard automorphic kernel. So on the left-hand side, I have standard automorphic kernel K of F. On the right-hand side, I have a theta series associated with this test function in the short space on this affine space. Okay, so now I can say more precisely what is this distribution, giving rise to the trace formula. So it's a relative trace formula for this for H prime and the other two and the subgroups H and H. So it's given by an integral of this kernel function Kf against a theta function with some additional weight. So eta here is a character, quadratic character for this quadratic field, and x is x here just means norm x here means determinant, so we raise the determinant to the s. Okay, and in general there's a lot of subtleties on the analytic side where these integrals may not converge and so on, but there's some way to regularize this to get a well-defined distribution. So functional of these test functions f and phi. Okay, so this is what we consider on the right-hand side. So on the one hand, this unfolds spectrally by the Flicker-Rallis period to give us adjoint L functions, these Asai L functions. And on the other hand, these unfold into orbital integrals, which we calculate and compare with the heights. So let me just skip to the orbital integrals and say what those are a little bit more precisely. So there's this so-called symmetric space, Sn, which is those the x in this GLN over the quadratic field with which satisfy x bar equals to 1. And so this has an action, say a right action by these the smaller subgroup H GLN by conjugation. More concretely, in the case when P is a split prime, this symmetric space is just going to be GLN of QP. Okay, so the orbital integrals will involve orbits in this space. Okay, so more precisely, if I take a pair, gamma and u, so gamma is an element of this symmetric space, and u is an element of this affine space. So this is just u will be a length n row vector with coefficients of qp. I'll take this to be regular, which means that the stabilizer for the h action is trivial. Then I can consider an orbital integral associated with some test functions. So f is a test function on the symmetric space over qp, and phi is some test function on this affine space over qp, which are exactly analogous to these global test functions f and phi defining this integral kernel and the theta function from earlier. Now in this setting, the local orbital integral is given by this formula, which is just the unfolding of this distribution from earlier. So there's an unfolding here where we integrate over h of qp of what looks like a usual orbital integral involving this test function f, but now there's an additional weight corresponding to this weight from the theta series from this test function phi. Okay, so this precise formula, I mean, we're not really used in any serious way in the talk, but I just wanted to write it down to give a maybe more precise sense of what's being considered. Okay, And so I want to consider the standard unit test, the standard test functions. So if I take f to be the characteristic polynomial of the integral points, and I take phi to be the characteristic function of the integral points of this affine space, and then I'll abbreviate this just by dropping the test functions. This will be my orbital integral. And so I'll compare this with heights of CM cycles, but after some normalization. So I'll write orb natural to mean that there's some normalization, which involves dividing this orbital integral by some explicit L factors and some explicit transfer factors. So I won't say what these are explicitly, but these have the property that these will be identically equal to 1 almost everywhere. So if everything is unramified, so if P is unramified, if gamma is integral, and okay, sorry, this is a typo. This should be this here should be the 2 by 2 matrix with this should be a 2 by 2 matrix with U on top here. So U is a row vector, and so gamma U is also a row vector. And so this will be a 2 by 2 matrix, and I'll require that its determinant lies in ZP cross. So some condition which is satisfied generically. Okay. Sorry about that. In any case, so this is my and so it's really this normalized orbital integral which will be compared with the heights on the intersection theory side. And another feature of the normalization that I wanted to mention is that, at least for the case of n equals to 2, this normalization makes the orbital integral satisfy a clean functional equation on the nodes between s and 1 minus s. Okay, so with this said, I can state the strategy a little bit more precisely. So before I had this distribution in relative trace formula, and so what the distribution is the derivative of this j function from earlier. So it's a distribution, meaning it's a functional of these test functions f and phi, which should somehow match this functional of the Heck operator t from earlier. And so on the one side, this should have some spectral decomposition given by adjoint L functions. On the other hand, it has some decomposition in orbital integrals. Okay, and now these orbital integrals, well, they unfold locally into local orbital integrals. This is the orb natural that I wrote on the previous slide. And the theorem, the proof, is local, so we make a turn-by-turn matching at each place. So in other words, I need to tell you how to match this with some local p-adic quantity associated with the heights of these CM cycles. So at least for the purpose of this talk, I'll call these heights of CMP divisible groups. So what we actually prove locally is that these log derivatives of orbital integrals can be associated with what I'll call heights of CMP divisible groups. There's some kind of arithmetic fundamental lemma here, where instead of comparing orbital integrals in one trace formula to orbital integrals in another trace formula, we make a comparison with this quantity coming from arithmetic intersection theory. Okay, so to make sense of this, I need to match these gamma u on the right-hand side with some quantity on the left-hand side. But this we already saw earlier when I decomposed the heights of the CM cycles of characteristic polynomials corresponding to CM cycles. So that's how this will match here. Okay, so so for the remainder of the talk, I wanted to explain this in more detail, how we make this comparison. But so up to here, are there any questions? Okay, so if not, then I'll continue. And indeed, this local comparison here, okay, so I started with the global picture and the relation of this height pairing with adjoint L functions, but it's actually this local picture here, at least from my point of view, how we really got started with this conjecture in the first place, where we first proved the local identity and then piece this together to get this global result. Okay, so I need to tell you what to match with these local p-adic orbital integrals. So as I mentioned, these will be what I call heights of CMP divisible groups. But just to make the analogy clear, I like to start with just usual heights of CM abelian varieties. So let's say I fix a pair, E comma phi. So this has nothing to do with the characteristic polynomial from earlier. This means the CM type. So E is a CM algebra, meaning a product of CM fields, and phi is a CM type. So some set of embeddings with some condition with respect to complex conjugation. Okay, now given this data, you can define a function, the Faltings height function, on this space of lattices. So I'll consider the space of lattices, maybe the set of lattices, z lattices, lambda, with complex multiplication. So what I mean by this is that if I take the Z lattice lambda and I tensor up to the complex numbers, then I equip it with an action of the CM algebra, which makes it free of rank 1. This is very much analogous to the case of, say, CM elliptic curves, where if I look at its H1 over Q, then it's supposed to be free of rank 1 over the quadratic field. Okay, so how do I define this function? Well, okay, define it in terms of abelian varieties. So if I look at the category of abelian varieties of the complex numbers, the complex multiplication by this particular CM type, this is equivalent to the category of Z lattices that I wrote above. The equivalence is given by taking H1 of the abelian variety. Okay, so given this, there's this Faltings height that I mentioned at the beginning of the talks. So I define this for CM elliptic curves. There's some way to generalize this to higher dimensional abelian varieties. In any case, the conclusion of this is that this Faltings height gives some arithmetically interesting function on this purely linear algebraic category of Z lattices with complex multiplication. Okay, so the next thing that I want to do is do something similar, but for p-adic lattices. So let's say I take a p-adic CM pair. So all this means is that, so EP here is some HL algebra over QP, so some finite product of finite degree field extensions of QP with total degree 2n. And this phi p is a p-adic CM type. So this just means some set of embeddings of EP into the p-adic complex numbers of size n. So unlike the number field case, I impose no condition about complex conjugation or anything like this. I just want this to be a set n size of embeddings. Now I want to consider something similar. I want to consider a function on ZP lattices with CM in the same sense as before, where it means if I tensor up to QP, I get something which is rank 1 over this HL algebra. And I want to define a height which is valued in Q times log P. Okay, and this will be done in a similar spirit as before, by comparison with CMP divisible groups. So, okay, if I have some CMP divisible group with CM by this particular CM pair, I can get such a lattice by taking its p-adic Tate module. This is not an equivalence, but if I pass, because there's not yet an equivalence, but if I pass to larger and larger fields, then this does give an equivalence of categories, very much analogously to the abelian variety case. Okay, so now to define this function, yes?
So I have a question about the same type.
Yes.
So your abelian variety have the same type, and the lattice you don't. Don't you need to fix the type of the lattice too? Otherwise, how do you know which one you?
Yes, that's right. So I fixed. So okay. So this function that I defined here will okay. I mean, maybe it's not so standard, but so this function that I defined here depends on the CM type. So I'm saying that after I fix the CM type, then I get a function on lattices like this. Whereas the function is just defined by looking at.
So in other words, you fix once you have that, you fix every CM type. You have isomorphism between the two.
Yeah. So for any CM type, then I get such an isomorphism. Yes.
Okay.
Thank you very much. So the same in the p-adic case, I fix the p-adic CM type once and for all, and then I get this, and then I get such a function. So for this, I want to define some kind of height, where I take a CMP divisible group and I output a number which lies in Q times log P. Okay, and so eventually this is what I'll compare with the orbital integrals. So let me try to explain what this is. So before giving the definition, to motivate, I want to explain a classical formula of Faltings, but how to compute the difference of heights between Faltings heights between isogeny and abelian varieties. So if I have an isogeny of abelian varieties, say psi going from A to B over the integer ring of some number field k, then you can calculate the difference of Faltings heights with this formula. So the formula has two terms. One is involving just the degree of the isogeny, which you can read off from even in the complex fiber. It has something to do with the Archimedean part of the height. And the second term is something to do with ramification on the integral model. So here I take the co-kernel. You can express this as follows. You can take the co-kernel of psi acting on the Lie algebras on the integral model. This thing has finite length because this map on Lie algebras is an isomorphism of the generic fiber. So you can take its size, and if you take a log and normalize appropriately, this formula calculates the difference of Faltings heights of A and B. And so for CM p-divisible groups, what we'll do is basically mimic this definition, but replace psi with an isogeny of p-divisible groups. So let me state this more precisely. So to do this, I'll fix once and for all a CM p-divisible group. So Y0, CM p-divisible group over, say, spec OK, with CM by the maximal order in this CM algebra that I had on the previous slide. And now I can define what I mean by the height, is height P of the p-adic height. Okay, just for this talk, the p-adic height of the CM p-divisible group. It's defined basically by replacing the formula from above with isogenies of p-divisible groups. And so the main subtlety here is that, unlike for abelian varieties, this is sensitive to the choice of isogeny. So for abelian varieties, there's already an intrinsic notion of Faltings height. So of course, this right-hand side, whatever it is, should not depend on the choice of isogeny, because the height of B is defined, height of A is defined, so the difference is defined regardless of what isogeny you take. But this local situation for p-divisible groups is more sensitive, so it depends very much on the choice of isogeny. And it seems like the correct choice to take is to take this psi to be a generator. So it turns out that this Hom space from the CM p-divisible group with a maximal order to this other p-divisible group is always free of rank 1. And so I pick a generator. So I pick a generator and make this definition. This seems to be the quantity that compares well with, say, orbital integrals. So, okay, this is a definition, but maybe the utility of the definition is that this decomposes the usual Faltings height in a canonical way. So here's what I mean. So let's say I have an abelian variety A with CM by the CM pair, but CM with possibly non-maximal order, then this Faltings height decomposes canonically into two terms. So the first term is its height in the case of CM by a maximal order. So in this case, if it has CM by a maximal order, the height does not depend on the choice of abelian variety. So some number depending on the CM pair. There's another term, a correction term, a p-adic correction term, involving correction, describing the discrepancy in the case of CM by non-maximal order. And so this is exactly this height that I just defined. So Tp of A is some p-adic lattice. So I can take what I was calling the height function of this p-adic lattice. So I get something valued in Q times log P. And so the conjecture of Kolmez is that this height of the CM abelian variety in the maximal order case, CM should be related with a log derivative of an L function. And so the local form of our result is that, at least in some special cases, and at least conjecturally, we expect that after averaging these correction terms over cycles, say on some local unitary Shimura varieties, these quantities should be related with log derivatives of orbital integrals. And so this is what I meant earlier by the comparison with something heights of p-adic heights of CM p-divisible groups with log derivatives of orbital integrals. Okay, so let me try to make this more precise in a special case. So I'll take V. Okay, so V to be a signature 1-1 Hermitian space. So this is rank 2. G is going to be the unitary group. And okay, so since I made, okay, G prime is this unitary group with a torus factor that I mentioned from before. So X is a Shimura variety, like from before. Here it doesn't, at the local level here, I don't need it to be compact. X could be I could take, for example, V to be, I could take G to be the quality split unitary group here. That's completely fine. And so I'll consider integral model at P. So I'll take P to be a odd split prime. I'll take the level Kp here to be maximal, in which case I get a smooth integral model over the integer ring here, which I'll base change. So the integer ring of the maximal ramified extension of Qp. Okay, in this case, well, there's a decomposition of orbital integral locally, and the intersection number also unfolds locally using the superseding the Rappaport-Zink uniformization. So let me try to state this a little bit more precisely. So let me write it down. So here I'll explain what everything here is term by term. On the left-hand side, this is the completion of this integral model along its supersingular locus. So at least if I pass to some neat level, I'm supposed to get some formal scheme. The formal scheme has a quotient description, which looks very much analogous to the usual adelic quotient description of to the complex fiber of a Shimura variety. So here, for complex uniformization, we'd have a complex symmetric space here. In this p-adic setting, we'll replace it with some p-adic formal scheme. In this case, will be some disjoint union of Lubin-Tate spaces. So the formal scheme, this Lubin-Tate space is just a formal spec of a polynomial ring. And in terms of moduli, this parameterizes deformations of the height 2-dimension 1 formal Petersburg group. There's a unique such thing over FP bar, and this space is parameterizing the deformations of this. Okay, and there's some away from there's some away from P part in the delicate uniformization. The quotient here is not by G, but rather by an inner form of G. So I have some inner form of G with a property that at the primes away from P, it's the same as G. But at P, if I look at P, it gives the units in the unique quaternion division algebra over QP. Okay, and in particular, this thing leaves its integers, the units in its integer ring, acts on Lubin-Tate space, and so I of Q will also act on the entire N because this is really a disjoint union of Lubin-Tate spaces. Okay, but so just to summarize, this is the unfolding on the intersection theory side, which is supposed to mirror the unfolding of the orbital integral into local orbital integrals. And so now I need a local analog of the CM cycles. So here it is. So if I take G in this division algebra integral unit, which is non-scalar, then I can consider the CM cycle, local CM cycle, which is the fixed points of this G acting on Lubin-Tate space. There's a local analog of the Hecke fixed points from earlier in the talk. And so this thing turns out to be finite flat over the base. And so now I can state what we actually prove in a precise form involving these local CM cycles. So as I mentioned, this trace formula strategy, we want to match something from the intersection theory side with something from orbital integrals. So the intersection number here depends on an element G. So it should also match with something on the orbital integral side. So the orbital integral depends on these gammas from earlier, and so the matching is by characteristic polynomials. The characteristic polynomial of G should match the characteristic polynomial of gamma. And so I also require this pair gamma U to be regular, so it means trivial stabilizer for the conjugation action. And this pins down the orbit uniquely. So in the special case, since I chose P to be split, I recall that the symmetric space is GL2. So here gamma is just concretely an element of GL2 with the same characteristic polynomial as this element in the division algebra. Okay, so now first there's a special value version, which is much easier. And then I'll explain the derivative version. So the special value version is that if I calculate the degree of the CM cycle, in other words, the degree of this finite flat morphism, okay, this is just a count of the geometric points of the cycle. This is given, okay, up to some factor here. So this is either 2 or 1, depending on whether this extension is ramified over QP brief. Yeah, so either 2 or 1, and times the value of an orbital integral, this orbital natural from earlier in the talk. And so this here is the local analog of what I mentioned earlier with these Hurwitz class numbers. These Hurwitz class numbers, we're counting degrees of CM cycles. So that's this. The left-hand side is the local analog of that. And these, I said, are related with orbital integrals, and so that's the right-hand side here. Okay, and so the derivative version is what's driving the what we can prove in the case of n equals 2 for adjoint L functions is that what I was calling the height, this height of C P divisible groups, is explained by the derivative of the orbital integral. So by the height here of the CM cycle, I mean to sum, it's a weighted sum, just like earlier. So locally here, I take a weighted sum over the CP points of the cycle, weighted by this what I was calling the height of the CMP divisible group. Okay, and up to some simpler factor, this is given by the derivative of this orb natural from earlier. And so okay, the last thing I'll say about this is that on the previous slide I said I should get a log derivative. Here I just have a derivative. And the reason for that is because for something like Faltings height, one typically defines it as a height like this, a weighted sum, but normalized by the geometric degree. So the Faltings height, for stable Faltings height, this takes the form of dividing by the degree of the number field. So in this local setting, we take this height and we divide by the geometric degree, then we exactly recover the log derivative that I mentioned in the previous slide. Okay, so this is our local theorem at the non-Archimedean place. Are there any questions here? Okay, so if not, then in the remaining time, I will say quickly sketch what we do at the Archimedean place, where we need to prove something as well. So first, okay, I should say, what is this Archimedean intersection number? So now we just forget completely about those heights of CMP divisible groups and start doing some analysis. I need to consider a harmonic Green's function. So this is my MathCal G for the diagonal class. So concretely, in this case, what this means is that G is a harmonic function, which is smooth, except maybe has some log singularity along this diagonal here. So F here is some local defining equation for this diagonal class. So where delta is locally defined by the equation F equals to 0. This thing is not unique, but it's unique up to adding a constant. And so now I want to explain the intersection number, associated intersection number. So for suitable Heck operators, so I'll take T to be an Eisenstein Heck operator, some technical condition here, which means I want to annihilate H0 of the Shimura curve. Or for these Eisenstein Heck operators, then the Archimedean part of this height decomposes as a simple integral. So it's just integral over the complex points of the Shimura curve of the Heck pullback. So this is the Heck operator acting on x times x. And I pull back this Green's function and I integrate it along the diagonal with respect, so I integrate along the diagonal with respect to the standard hyperbolic measure on the upper half plane. And so in general, for general Heck operator T, this intersection number will be more complicated. There'll be another term involving an integral over x times x, but for these good Heck operators, which are Eisenstein, you can kill the second term. Secondly, another advantage of taking this Eisenstein Heck operator is that the Green's function is only defined up to a constant, but if I take this T to be Eisenstein, it'll kill the constant, and so it's completely unique. Okay, in any case, this is the Archimedean part of the intersection number, the integral of some Green's function, and these Green's functions were studied by Gross and Zagier, and as a consequence of their work, you can show that this can be unfolded into and expressed in terms of orbital integrals. So there's some regularization here by parameter nu, so I won't be say much more about that. But the point is that this unfolds into something which looks like it fits into a trace formula. So it unfolds into some orbital integrals, so there'll be some Archimedean orbital integrals and also some non-Archimedean orbital integrals. So let me say what Q here is. So Q here is just a Legendre Q function, some special function. And so the key point I want to make is that it's a test function with singularity. So Q here, as a function of one parameter, has some integral representation, which I won't really use. But the key point is that it has singularity as t goes to 1. So, okay, I said I should get a test function on u11. This is a function of one variable. And so you can upgrade it to a function on u11 using Cartan decomposition. So you can upgrade it to a bi-k invariant function on u11, where k here is a standard maximal compact. And so the reason is that if after taking this two-sided quotient, you get something which is one parameter corresponding to a diagonal. So you like the diagonal torus in SL2, and so this one parameter, will correspond to this one parameter t. So this Legendre Q function then gives a test function with a singularity along this compact along k infinity. Okay, so I have this test function, and so what we want to do is compare this orbital integral with the derivative of an orbital integral on the GL2 side. So let me state that more precisely. So we like to compare this orbital integral with the derivative of an orbital integral on the GL2 side. And okay, so I'll say more precisely what this is. The right-hand side is, so I need a test function. This is a transfer from the constant function on compact U2, essentially considered by Mihach, Sankaran, and Yang. And so it has a property that this orbital integral is 1 if gamma is elliptic and 0 if gamma is hyperbolic. That's what I mean by a transfer here. And so the key point here is that we want to know about the derivative, but we can transfer this to a statement about a special value. So here's what I mean. So I have this GL2 orbital integral, but there exists a test function on the unitary group with singularity with the property that, so for matching orbits, the value of this orbital integral is equal to the derivative of the orbital integral on the GL2 side. So this way we transfer a statement about a derivative to a statement about a special value. Explicitly, this function can be described by the EI function, just like before. So it's just like before, this turns into a test function on the unitary group using the Cartan decomposition. And so I've transferred the statement about a derivative to a statement about a derivative on one group with special value in another group to just a comparison of orbital integrals, two orbital integrals on the same group. Okay, so now it's my very last slide. I will sketch how this goes. So here is again, we want to compare these two orbital integrals for these two functions. This is not done by by an exact comparison. So these are not equal on the nose. Instead, we do the following. So I mentioned that these both are test functions with singularities. And so while they're not the same test function, their singularities cancel. So if you subtract the two functions, okay, with some constants, the singularities cancel, and this function extends continuously to the point t equals 0. In other words, if I use Cartan decomposition again to get a test function on the unitary group, this gives an honest continuous function without singularity on the unitary group. And one can also check that this test function now has enough decay to run the Selberg trace formula. And so by Selberg trace formula, if I calculate the difference of these orbital integrals and put it back together globally, what happens is that this orbital integral can be expressed as, in terms of the traces of these operators acting on automorphic forms, say L2 automorphic forms. And so, but the key here is that phi here is bi-k invariant. So if I take the trace on an automorphic representation, the trace should only be non-zero on those representations with a non-zero k fixed vector. But in our trace formula, in our theorem, we were really interested in the representations for cohomological middle degree. And those Archimedean parts will be either holomorphic or anti-holomorphic discrete series, but do not have any k-fixed vectors. So while these two are not equal on the nose, for the purpose of trace formula and extracting information about these cohomological representations, their difference is 0. So this is roughly their strategy in the Archimedean place. Certainly, there's more technical details here, but for the sake of time, I should stop here. So thank you very much.
Thank you very much for the talk, Ryan.